So we've got the digestive system today in your memory section. So again, skipping forward a little bit, like we just went from the respiratory system, and now we are diving straight forward a couple chapters into chapter 19, the digestive system. So looking at this today, what we're going to be going over, we'll talk a little bit about the general organization, the segmentation of your digestive system and all the various different organs, your digestive tract there, accessory organs that kind of spit stuff into the digestive tract, how digestion works, how absorption works. We won't spend too much time talking about how it's all like regulated through like, your nervous system and your hormones and stuff. We'll mention it briefly, but not too much of it's going to make its way into our notes. Same thing with disorders. We won't spend too much time on that, or the effects of aging and stuff. So looking at your digestive system, which, is another support system, right? If we think of it as the way that it supports our ability to move, right? It's supporting the human movement system. So this one is designed to break down and absorb nutrients for energy production. So that's the key thing here, right? We are taking food and breaking it down into little components, and then we use those components to build them up into something else, something U-shaped, not the letter U, the Y-O-U. And so, the three parts of digestion, or the three main purposes of the digestive system, rather, are going to be digestion, which is the process of both mechanically and chemically breaking down foods, right? So chewing is mechanical, but then your stomach acid is chemical. And so this is a very catabolic process. Takes these big complicated pieces of food, breaks them down into individual components so that they can be built back up into something else. Think of it as like, disassembling a house into like bricks and, slabs of wood and, nails and screws and things like that. Once we've got them all broken down, now we can reassemble them into some other shape if we want to. Then we've got absorption, which is the process of getting those nutrients to pass into our bloodstream. So when you think about like, your digestive system, it's actually very much on the, I know it's inside, but it's kind of on the outside of our body. So we got to be able to get stuff that's small enough to be able to pass into our bloodstream, similar to how, we had these like branches and branches and branches and branches inside of our lungs that eventually ended in those little sacs that are covered in blood vessels. And then oxygen molecules just passively move from one side of a membrane onto the other, move those oxygen molecules onto our red blood cells. The red blood cells are still inside the body. The oxygen was outside the body until it passed through that wall. Same thing is happening with absorption, exactly the same thing, except this time it's, proteins, fats, and carbs. So that's going to allow those nutrients to go from an external environment to an internal one. And then we got the process of elimination, which is, getting all that stuff outside the body. So we've got a lot of like our digestive tract here, which is going to be, where all of this takes place. Then we've got accessory organs that make the whole process easier. So looking at your digestive tract, and kind of labeling it out here, we're going to talk about how it moves basically from your mouth to your pharynx to your esophagus, down into the stomach. Then it moves through the small intestine pretty slowly, absorbing different materials. This is where, all of this was really involved in the idea of like digestion. This is where we start to really get into absorption. And then a large intestine is some final absorption before, again, we have the elimination aspect of it, right? So you can see here's the digestive tract here. So your digestive tract is this hollow tube that allows food to be transported through the body from the mouth, and it's trying to get to your large intestine. Because that's where it's going to be eliminated. And along the way, we are going to digest stuff primarily, in the stomach. And we do a little bit of digestion here in the small intestine as well. Make no mistake. Chemical digestion is taking place primarily in the stomach, but there's actually a good chunk of it that does happen in the small intestine. And then we sort of switch over to the process of absorption. Like once all that stuff's broken, it can fit. Again, kind of similar to, we broke down a house into its individual components. If you think about like the ability to absorb something, if you've, has anybody ever made this? So, all right, so here's the perfect reverse. This is actually an analogy, but it's in reverse. So my dad's a furniture mover, right? And I used to work at his moving company. I started when I was like 16. And, I used to work for him every summer. And, anytime I had school off, I was, I had to go on a job and stuff. My senior year, actually, I finagled my schedule to have Tuesdays and Thursdays off in school. And I was like, great, vacation time. I can play video games and stuff because I was a high schooler. And my dad made me work at his company instead. Just what I get for being, sneaky with my schedule. But that is, here's a common thing in the moving industry. This happens all the time. You go to somebody's house and they'll have this huge piece of furniture. And you'll look at it and then you look at the door and then you look at the furniture and you're like, did you get this through that door? And they're like, oh no, I bought it from IKEA and I assembled it in here. I put it together. Do not make this mistake, everybody. This is life advice that has nothing to do with personal training, but here's my advice to you. Always measure out how large your furniture is going to be. Do not assemble it in the room. Because if you do, you may not be able to ever get it out again. And that happens all the time. That's sort of what absorption is kind of like. If you've got these things that are way too large to be able to fit through the door, it's not going to be able to get into your bloodstream. So when you think about like, when you think about like someone who's lactose intolerant, lactose intolerant people, they get muscle cramp, they get like stomach cramps sometimes, they get kind of gassy sometimes. And the reason that happens is because their body lacks this specific digestive enzyme that allows them to break down lactose. That's why they are lactose intolerant. They're not actually allergic to lactose, which a lot of people kind of think lactose, and it's like, oh, it's a milk allergy. It's actually not an allergy. It's not your immune system that's doing this. It is actually because this little sugar, which is found in milks, doesn't get broken down. And so because it doesn't get broken down, it stays a double sugar molecule. It stays as a disaccharide. And it ends up passing through your digestive system without being able to be absorbed into your bloodstream because it's too big, which is crazy. You think about like it's too large. And this is just a molecule of 2 sugar. I mean, like if we look at like glucose versus lactose, it's just that's a molecule of glucose that it's just a single, I'm sorry, that's galactose and that's glucose right there. These are just 2 little individual sugar molecules. That's not that big, but it is just large enough to not be able to fit through the holes in your small intestine. So it can't get into your bloodstream. So what ends up happening is it just survives. It just like stays uninterrupted, works its way through the small intestine, and then eventually gets into your large intestine. And here at the large intestine, this is where all your gut bacteria lives. And, gut bacteria feeds on things like sugars. And so when that like lactose gets in here and it's just this already somewhat broken down sugar that's really easy to like process, by a bacteria at least, the bacteria goes nuts and it starts like eating it like crazy and doing all this like, reproducing and stuff. And so it ends up creating like a lot of gas, which then, fills your large intestine, might lead to cramping, might lead to gassiness, all these things that you'll sometimes hear people talk about when they drink too much milk. So, your digestive tract, this is, just looking at that, you can understand why it's so important to be able to break everything down. And we do have like a lot of accessory organs that are going to help with this process of breaking stuff down, right? So these are basically organs that are attached to your digestive tract. Their job is to like secrete different like juices and things like that into the alimentary canal, into the tract here to allow for the breakdown of stuff, right? So for instance, your liver creates this stuff called bile, and bile is what breaks down fats. Your pancreas is going to create things that help break down actually fats as well, but mostly carbohydrates, right? All those little things are really important little accessory organs. So let's go ahead and go through the alimentary canal here. Let's go on a journey. So we'll start in the mouth, your oral cavity, if we're being all fancy. And this is where like the first process of like digestion is going to take place. This is where we have a little bit of mechanical processing, right? The process of chewing uh, is actually going to start breaking down food, both mechanically and chemically, actually, because your mouth is going to start mixing with like your saliva, right? Or your food's going to start mixing with your saliva, right? And so you've got like the mechanical process. Your teeth are chomping everything up and taking large chunks and breaking them into smaller chunks. But then we've also got this stuff in our saliva called salivary amylase. This is actually an enzyme. And it's an enzyme. Remember enzymes, when we talked about them at the very beginning of this class, enzymes they don't have any energy of their own. They're little proteins actually, without any energy. But what they do is they kick off chemical reactions, right? They're like the key in your car. Doesn't have any gas, right? But it allows your car to use that gas. It starts the usage of that gasoline. So, these enzymes start to break down carbohydrates, and carbohydrates is big, long, complicated chains. We start breaking them down with our saliva. Now, your saliva is not so good at breaking them all the way down, but it can break these big, complicated carbohydrates into double sugar molecules. It can get them down into disaccharides, and that's why stuff tastes so sweet when it's on your taste buds. So your salivary glands are what are secreting that saliva, and that has all that salivary amylase. It makes it easier for you to chew stuff up, but it also starts to deglutition those sugars. It starts to break them down into double sugar molecules. Then we're going to pass into the pharynx, which is a big fancy way of saying throat. And then that's going to, have a couple different divisions there. You've got your oropharynx, which is the mouth part of it at the very back here. And then you get your nasopharynx, which is where your mouth connects to your nose, which is where if you've ever seen someone like, laugh while they were like trying to drink something and it squirted out their nose, that's because those are one connected tube. And then you've got your laryngopharynx, which is where your vocal cords are going to be located. That's going to connect to your esophagus, which is this muscular tube that runs from the mouth down to our stomach. So we got to be able to get stuff here. There's no digestion here. This is really just, sort of a junction. But what's really important about the esophagus, or what's one of the things that's kind of fun about it, is it does actually pass through your diaphragm. Remember, we talked about the diaphragm is that muscle that contracts to draw air into our lungs. Well, your esophagus passes through a little hole in that muscle there. And so, when you start to get older, this is one of the effects of aging, is that sometimes it actually gets harder to swallow stuff because this tube is slightly muscular. It's smooth muscle, but it's still like contracts a little bit. And it does this process called peristalsis. And peristalsis are these little wave-like contractions that move food throughout your digestive tract. But some of it happens in your throat. You've felt this before. If you've ever swallowed something too big and you felt it like drag the entire way down and you're like, oh God, right? Took too large of a bite, right? You can feel peristalsis you can't really feel the individual little wave-like contractions, but you are feeling it like slowly slide down and kind of hurts a little bit. But peristalsis is the little wave-like contractions. I always think of peristalsis as like when I'm at the end of a tube of toothpaste and I'm doing that thing where I'm like, come on, there's got to be just a little bit left in there, little tiny squeezing it to the end. That's kind of how we move food throughout our digestive tract. So that's your esophagus. Then it's going to attach to your stomach. The stomach is this really cool little J-shaped pouch. And this is filled with hydrochloric acid, actually. So when you look at your stomach, you'll see it's actually several different layers. And these layers here, actually, they kind of go in different directions, which is good because that allows your stomach to kind of protect itself. But it also has all of these really cool like tissues that make a lot of really interesting materials. So for instance, like your stomach is constantly like, secreting hydrochloric acid, but it's also creating things like gastrin and pepsin and digestin, all these enzymes. So your stomach acid is hydrochloric acid, right? Which is, by the way, it's so acidic. And I know I've said this in previous classes, but for those of you who haven't heard this, it is so acidic. If you were to pull it out of your stomach and pour it onto your arm, it would actually give you a chemical burn. That's how acidic this material is. And so, luckily none of us can scoop that stuff out, but your stomach is very, very, very acidic. And it's not just stomach acid. There's other materials in there. There's a lot of enzymes. There's pepsin, which is going to help, an enzyme that helps break down proteins. There's gastrin, digestin. There's a lot of different enzymes in here. And so what's happening is there's just a ton of chemical breakdown of food and materials, right? And so because of all that chemical breakdown, hopefully it's going to get into this, very wet, soupy mixture once we're done with it, right? Mixed with a little bit of water. And now you've got this like nothing but little tiny particles. And, if some of them are all the way broken down, then you've got nothing but chemicals. So they can just pass right into the bloodstream because everything's very, 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 very small now. So in your stomach, right, like I said, it is like filled with all these like, acidic chemicals and enzymes and stuff. But you're also going to see these little folds inside of your stomach called your rugae. And the rugae are these little, the muscular walls actually contract to move foods around. You have heard this if you've ever laid on someone's stomach and then like, they're like, like all that stuff that you're hearing, you're hearing all the contract. Or if you've ever been like, after like digesting food and your stomach's really loud and stuff, that's your rugae at work. And it's basically there to like contract and move stuff around and make sure that all the food we consumed really gets like a solid acid bath, So that is the different layers there. Now, one other thing that your stomach does make as well that we need to be aware of, it also makes a lot of mucus, which is really important because mucus is very base. You think about the pH scale, you've got your acids and you get your bases, right? And so mucus is sort of on the opposite side of the pH scale. And so that balances us out and makes sure that like that stomach acid does not ever like digest through and eat our own stomach, which it could do, if it didn't have anything to prevent that from happening. And that's where you get like ulcers, If anybody in here knows somebody who has an ulcer, that's where sometimes stomach acid will get up to the esophagus here, or maybe it'll burn through parts of the stomach because maybe it just got to a place where, there wasn't enough mucus. And so that stomach acid was exposed to, regular tissue. So that's your stomach. The next part is, and its job is to like store food, secrete all these gastric juices that I just talked about. And then once that happens, like all of your food's going to be fully broken down. Well, not fully broken down, but it's broken down. It doesn't really look like chunks of food anymore. Like if you, it's gross, but if you like chew something up and they're like, bleh, right? It still looks like food. It just looks like, messed up food. But by this point, all of that food has mixed together with all these different acids. There's been so much chemical breakdown. We don't really consider it food anymore. We have a special name for it. We call it chyme. And chyme is this like, again, like wet, soupy mixture of really just chemicals at this point, right? So that those chemicals can pass into our bloodstream. So now that chyme is going to get delivered to your small intestine. And so your small intestine has several different divisions. The first part of it's your duodenum, which is where it's sort of connected to the stomach there. And in that section, there's going to be a little bit more digestion that takes place. Anything that happened to survive your saliva and chewing, and then anything that survived your stomach acid, there's a little bit of like digestion of a little bit of proteins, a little bit of carbohydrates that are happening here in the small intestine. And then you've also got the delivery of bile here, which we'll talk about in just a second. But bile is this material that starts to really break down fats. Fats don't break down in acids very well. It doesn't have a very like strong effect on those things. So when you eat like a really fatty meal, it doesn't really sit in your stomach for that long because a lot of that fat can't be broken down very effectively. It's just not the organ to do it. So what has to happen is we have to break that fat down in the small intestine with the help of the liver. And so the liver is going to create this material called bile, and then bile is going to be dropped off in the small intestine, and then that's going to actually digest all of those fats. So, you know, the small intestine still does do a little bit of this process of digestion, but what it's famous for is absorption. You know, when we get to the later segments of the small intestine, there's going to be some maximal absorbing that is going to take place. And the reason for that is because it has a massive, massive, massive amount of surface area. So you can see here, if you look at your small intestine, right, here's like, we're just looking at like a little, you know, here's the small intestine kind of, you know, zoomed in, right? We see like there's one of these little sections of the tube, and then you see how it has all these little folds on it, right? If we zoom in on like that, like crazy, you'll see those folds, they look a lot larger. And then each of those folds has a lot of other folds on it as well. And then if we zoom in on that, you can see those folds have little blood vessels that come up on them. These look like little hairs almost. You know, the little hairs on folds. And then there's actually more hairs on top of that, which are called your microvilli. And those little hairs are actually what are moving materials around to make sure that, you know, these nutrients can get exposed to the right sections of a blood vessel. So, you know, like folds on fold, you know, we had bundles of bundles of bundles with our muscle fibers. Well, these are going to be folds on folds. Lots of like little itty bitty layers here. And so you think about it like, I always do like a bad paint drawing here, but you know, it looks something kind of like this. It's like there's a fold, and then like there's a fold, and then there's another one. And then on each of those, you know, you're going to have all these little itty projections. These little projections are called your villi. And the villi are really where the absorption process is taking place. I'm going to go ahead and do this for like another 3 seconds and not continue the whole thing. And so like then you're going to have, you know, little blood vessels in here, you know, little like capillaries, and those capillaries are going to act as sort of like the exchange site for those nutrients, right? And so, you know, everything's going to get into the bloodstream through right here. And then there are little tiny hairs called microvilli. They're also straddling each of these individual little villi there. So those little microvilli just kind of move things around. They're cilia, just like the cilia around our cells. Remember we talked about how like that basically like it's the hair surrounding your cells that move stuff from so it can get into the right spot, and then eventually gets to, you know, like a channel or a pump or a hole or something, you know, gets sucked in. So, you know, and that is everywhere in your small intestine. And the reason for that is because it just creates a massive amount of surface area, you know. Like, let's see, I looked this up once. What is the average surface area of the small intestine? About 250 square meters. Okay, 2,700 square feet. All right, so the average children's, I wonder if that's right. Whatever. It's still super large, so it works for what I'm trying to prove here. You know, the amount of surface area that you have in your small intestine, like your small intestine, how long is the small intestine? Small intestine's about 22 feet overall, right? Which is huge, you know? But like as much as large as that is, imagine if you just had to paint, again, kind of going back to that conversation of surface area. Imagine if you had to paint the inside of your small intestine. It's 22 feet long, you know, if you stretch the whole thing out from end to end. And then you just, you know, painted the inside of it. No, take about 22 things worth of paint. But because of this arrangement right here with all these individual little folds, it increases the surface area by a huge, huge margin. And that's why we're going to see, you know, 2,700 square feet worth of surface area, which is massive, you know, and that allows all of these chemicals to really just have plenty of opportunities to kind of pass right into our bloodstream. So they say that if you were to feel the inside of the small intestine. It has a texture kind of like velvet. All those little tiny hairs super tightly packed together. Not that you should ever have an opportunity to do that. So the small intestine, long hollow tube that's responsible for absorption. It does have these large folds on them, which we call lumen. And on each of the lumen are, that would be this big fold right here. That's a lumen. And then on each of those, there are those little individual little tiny hairs or, more folds, which are called your villi. And the villi are these microscopic folds. They are filled with blood vessels. This is the actual absorption. And then they house the microvilli. And the microvilli are not really folds. They're just the little hairs on the outside of all the villi. They're cilia, right? And so they're going to move nutrients around and allow them to get to the right part. So then if we look at the role of your small intestine, right, it's got the microvilli, which again, your villi and your microvilli, that's just maximizing surface area. You've got a ton of surface area, which just allows so many nutrients to easily pass right into our bloodstream. Then we have your large intestine. So I'm going to come back to this in just a second, but your large intestine is the final part of the sort of alimentary canal we've been talking about here. This is going to absorb a little, anything that didn't get absorbed in the small intestine that still may be able to. Some of it might pass through in your large intestine. Minerals and electrolytes, for instance, do a pretty good job of getting absorbed in the large intestine. But a lot of the water content. And so there's a ton of water content that is going to be absorbed by your large intestine. So, this is where you're really kind of like getting a lot of that water back, because water's been around this whole time, really just making it easier for nutrients to kind of transport and move around. But we need to get them into our blood. We need a lot of water in our bloodstream. And so your large intestine is really going to absorb any of those final products, a lot of the electrolytes and stuff, your B complex vitamins and things like that. And then, your large intestine also secretes things like mucus, which is, not getting too and try not to get too nasty here. But like I said, it's gonna form your feces and then, get that all out of your body. And so your large intestine is going to, chyme was this wet, soupy mixture. And your large intestine is going to pull all of the water out of that chyme, which is going to dehydrate all that stuff. And that's what's going to make your stool. And then, you're going to get that out of the body. Really quickly, taking a look at some of our accessory organs, because the digestive system goes in such a weird order when we're kind of writing it all down. But inside of, if we look at the accessory organs that we've got here, right? You do have a ton of accessory organs that are secreting these different materials that are making this digestion and absorption process easier, right? You get your salivary glands, which you can see here. You've got your parotoid gland, submandibular. Here's your sublingual one. That's the one you've ever touched it by accident, like stuff shot out of your mouth. That's your sublingual. You can thank your sublingual gland here. But all these little glands are just secreting that saliva, right? And so these are all there to release that saliva that has all that salivary amylase and stuff. And so moistens your food. It allows you to start chemically breaking down carbohydrates, all kinds of good stuff. Moving down from there, you've also got your liver, which is one of the most important organs of our body, right? And so the liver is an accessory organ that it does a ton of stuff inside the body, but it also really assists with this digestive process that's taking place outside the body, right? And I always say that, but again, like remember, human donut analogy, right? You're an uninterrupted donut from mouth to exit, we are absorbing stuff from that outside environment to the inside. Imagine if you didn't have a digestive tract, but you just had to absorb stuff through your mouth. You'd put something in there and like let it sit for a couple hours and it would pass into your bloodstream and then you'd be like, bleh, and like spit it back out. Kind of like owls, a little more complicated than that. But looking at your liver, right? Your liver is an accessory organ that does interact with your digestive system, primarily because it is responsible for manufacturing what is called bile. And so bile is basically this emulsifier that breaks down fats. So the way I always describe it to people is if you've ever, if you've ever made like a thing of like ground beef or even just like a steak or something, you've got like a really greasy pan. If you run it under hot water, it doesn't really do much, right? Because water and lipids don't mix. So you need something to break up those fats, right? And water and lipids don't mix because of when we looked at like phospholipids. Remember we were talking about our cells, right? Our cells are these phospholipids, right? These these little glycerol molecule with two little lipids attached to it, two little fatty acids, right? And if you dump a lot of phospholipids in an area together, or any other type of lipids together, they all kind of arrange themselves together like this, with the alcohol side, which is what we call hydrophilic, it likes water, in this side, and then the hydrophobic sides, which hate water, towards the inside. And this is why water cannot penetrate. You can run water over like a fat all day and it really doesn't do much, it doesn't really ever mix with it. And that's what we're seeing right here. That's the arrangement that gives your cells all of their shape. Well, bile allows you to break that down. Bile acts as like an emulsifier. So we look at like emulsification. Yeah, I guess this is fine. This is fine. So we have like a fat here, right? A big fat, and then we drop some like dish soap onto it, and it breaks it into little individual like little droplets, because it's able to break that arranger, that structure. So that is what we are going to see. There we go. Actually, this is great. So you can see there's a very stable fat. You drop some dish soap in there and it'll make it all very unstable. It'll emulsify it. And then suddenly it can kind of, mix with our liquids and stuff. So that's what your liver does. Your liver makes bile. It also has a lot of other jobs, right? It stores glycogen inside of your body that it can release back into your bloodstream if your blood sugar levels ever get too low. It modifies your fats, it stores vitamins and iron and things like that. It also kills your old red blood cells in the coolest named thing inside of your body, which is called the red blood cell graveyard. When blood cells get too old, they eventually travel through the liver for detox, and the liver eats them up and then sends the ingredients back to your bones, and then you start making new red blood cells. So they are reborn as a young, healthy red blood cell. It also synthesizes your urea, which is how we get our urine. So your liver works together with your kidneys to create your urine and stuff. But for the purposes of talking about the digestive system, like I said, the main thing that it's going to do is it's going to create your bile. Now, bile is not dropped off into the small intestine directly from the liver. You have a little other accessory organ called your gallbladder, which is actually going to store your bile. And so once your bile is manufactured by your liver, it will basically store any excess that it makes into your gallbladder, and then your gallbladder's job is to drop that bile off into the small intestine. So this little tiny organ, you can see it right here, that secretes that bile into your small intestine so that it can modify those fats. This is why you probably, everybody in here probably knows somebody who's had their gallbladder removed. My mom had her gallbladder removed. And so basically, like what that is they got a really bad gallstone. Sometimes materials from the liver get stuck, get put into the gallbladder, and then, they're minerals and stuff. And so they start forming together with other minerals until it makes this like, kind of rock. That ends up like blocking the duct that leads to the small intestine. So that little stone, if it ever gets dislodged and lands somewhere over here, now bile cannot, move from here, and there's a big traffic jam, right? It gets made in the liver, dropped off in the gallbladder starts stretching out because it can't really hold anymore, and it feels extremely, 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 extremely painful. So doctors have to go in there and they got to remove this organ because there's really no saving. They don't have the ability to kind of open it up and extract it or anything. So they just have to cut it out. And then what they do is they just attach a duct directly from the liver straight into the small intestine. So you don't have any backup storage, which means if you've ever known somebody who has gallbladder surgery, you know, they can break down fats just fine as long as they don't go crazy, getting like massive, massive, massive amounts of fat in at a time. Then, you know, then it can start to cause like little bits of problems there. Now, I don't want to spend too much time on this next part, but just really quickly talking about the process of hydrolysis. This is something that, you know, this may come up in your notes. I don't think it does. I think that's the other class. But just talking about it, right? Breaking down what hydrolysis is, right? This is a hugely important metabolic process. So hydrolysis is basically where you are using water to break stuff apart. Okay, so it's saying, you know, hydro coming from the word water, lysis coming from the word, I think, destruct, or maybe just like breakdown. But you look at like here's a double sugar molecule, right? Here's a disaccharide. Now, if you add a little bit of water to this, it may break it up. It may break this disaccharide down into 2 individual pieces. But if it isn't able to, it'll maybe need an enzyme in order to make that process really, you know, start to happen. But regardless, like this is how you can make things like simple sugar, right? Anybody in here ever made simple sugar? Anybody at all? You just sugar and water and you just mix it up and then you can, you know, put it in your coffee or whatever. So simple sugar is basically, you know, the way that you make it is you put a lot of sugar in some water and you turn the temperature up just a little bit. And the heat kind of acts like an enzyme. It's, you know, it's not an enzyme, it's just heat, but it is able to unfold those sugars and break them down into individual little single sugar molecules. So hydrolysis is doing this because if you think about it, and I'm just going to actually, here we go, print screen, go to Paint. Let's kind of show this happening in real time. So, and then I'm just gonna steal that and paste right there. Okay. So hydrolysis, right, is where you take a molecule of water, right, and we look at like what water is, right? Water is H2O, which really means that it's 2 H's and an O, right? So that's a molecule of water right there, H plus O. Okay. Now, if you look, right, you see that this double sugar molecule is held together right here with a molecule of oxygen. So oxygen's what's holding this molecule together. It's what's allowing these 2 separate individual molecules to be attached together. There's a little bit of oxygen binding them in the center. So they would be just as happy little stable molecules if they ended like this. If this one ended in an OH pairing and this one ended in an HO pairing, you know, which would, you know, is what we see on the other side, right? See this right here is actually identical to that right there. You know, that would be just as happy. They would be just as happy if they look like that. So if there's water in the area, what might happen is this H might shove itself right here. God, I did that badly. This H might shove itself right here. And now this side of the sugar molecule is happy because it's got an OH pairing at the end of it, right? And then this H, it might shove itself over here. And this O, it might shove itself right next door. So now with this little O here, this O here, this H here, and this H here, you've got, you know, basically this guy is here. This guy is here. And this guy is right here. So now you've got 2 individual little happy molecules. I know this got messy when you look at it all overall in the end, but like that's the process of hydrolysis. That's how water breaks stuff down. This is happening in anytime you've like, you know, you've eaten oatmeal and, you know, you didn't get the bowl to the sink very quickly. And so it gets all crusty and you're like, oh, I'm going to let that sit under water for a few minutes. So you pour some, you know, you fill the bowl with water, you let it sit for 10 minutes, and then you go in there and you wipe it right off. That water is basically shoving itself between all the little molecules that are holding those oatmeals together. and, sticking them to the side of the bowl. So you put a little water in there, and then all these OH and HO pairings are breaking those things up. And that's why it's so easy to wipe it off. That's hydrolysis in a nutshell. So hydrolysis is a catabolic reaction, right? Remember when we talked about metabolism? You've got anabolic, which is building stuff up, and you've got catabolic, which is breaking stuff down. Hydrolysis, by the way, is the most common catabolic thing that happens in this universe. Water is, they sometimes call it the universal solvent. And that's because like it is in this universe that we live in, it is better at breaking stuff down than any other material in the universe. And I know that we just got done talking about stomach acid, and you might be being like, wait a minute, like acid's great at breaking stuff down. Yeah, acid's really good at breaking certain things down, but water breaks more things down. Certain materials do not break down in acid at all, but water eventually gets to everything. So that's kind of a fun one for you. So let's go ahead, now that we got all the working parts in order, let's kind of go through the process of digestion step by step, right? So you're going to start by chewing food in your mouth. There's a little bit of like mechanical digestion that's taking place. And then that food is mixing with your saliva, which has all this salivary amylase in it. And that salivary amylase is going to break down any carbohydrates in that food down into sugars, not full glucose molecules, not single sugar molecules, but disaccharides. It'll get it down into little double sugar molecules. And so there's a little bit of chemical digestion that does take place there as well. Then your stomach is going to secrete, it's going to pass into your stomach, where your stomach is secreting hydrochloric acid and a whole bunch of different types of enzymes, pepsin, digestion, gastrin, whatever. And then it's also secreting a little bit of mucus to make sure that your stomach doesn't digest itself. That is going to break all that food down into chyme. And then chyme is going to pass into your small intestine, where that is going to be mixed. Your gallbladder is going to drop off a little bit of that bile, which was created by your liver in order to emulsify fats. So the fats that didn't get broken down by the stomach are now in the small intestine, and that bile is getting mixed in. And now you've got carbs broken down, you've got proteins broken down, and you've got fats broken down. And so now everything is fully, really broken down. And then that chyme, that wet soupy mixture, is going to kind of work its way, flow down the small intestine there, where, materials are going to be sucked into your bloodstream, thanks to all of the little villi, which are the little projections, little like wavy, foldy hair things that are projecting from your small intestine. And that's going to have a lot of blood cells inside of them. A lot of blood vessels inside of them. And so those materials are going to pass through those walls into your bloodstream, similar to how oxygen passed through the walls of your alveoli, So that's going to pass into your bloodstream. And so now you're absorbing anything from that chyme that, really can be absorbed. And so there's not much left in there in terms of like nutritional value. So then, that is going to work its way into your large intestine, where your large intestine is going to absorb a few vitamins and minerals, by the way. Like, actually, really quickly, going back just a little bit, when we're still in the small intestine, you are going to absorb a lot of your vitamins, particularly your fat-soluble vitamins. So vitamins A, D, E, and K in particular. Those are fat-soluble vitamins, which means they are transported with the help of fat. And so because you have fat in your diet, that's what's allowing those vitamins to be carried into your bloodstream. Unfortunately, they can't really get through the wall without it. It's like when you're waiting outside a club and you have to go, your friend has to be like, I'll let you in. That's kind of fat soluble vitamins in a nutshell. Water soluble vitamins need water. They pass through pretty well, but they are better absorbed by the large intestine, because the large intestine does most of the heavy lifting when it comes to absorbing water. So your fat soluble vitamins are getting in, in the small intestine, and minerals as well, kind of in both places. Back to the small intestine here. So now you've really absorbed everything, and now everything is going to pass into your large intestine. Your large intestine is going to absorb a lot of water. And so a lot of that water is getting pulled out. Water-soluble vitamins are going with it. But because of that, because water, because we are dehydrating this chyme, if we go back to this, right? Remember, this was hydrolysis, where water shoved itself between these two molecules in order to break them apart. And then you've got two, separate individual sugars here, right? Well, imagine that process in reverse. If you were to take this H and suck it out of there, and then this O, and pull it out, and then pull this H from here, right? Now you've got H2O again. So now you've got a water molecule that's left over. And what will happen is this will become attracted to each other again, and they will end up linking back up. This is how your metabolism deassembles stuff through hydrolysis and reassembles stuff through what we call dehydration synthesis. If you've ever heard the word synthesis before, you know that it means to make something, right? I'm synthesizing the antidote, that's you're making something, you're synthesizing it, right? Dehydration synthesis, that's how we are doing this. We're basically dehydrating something to allow it to be attracted together again. This is why your stool is solid, and it came from this wet, soupy mixture. Now, again, this is going to get a little gross, but you've definitely experienced at some point in your life where, maybe you ate the wrong thing. Maybe there was a virus or a bacteria probably in your food, and your immune system discovers it, and your immune system is like, whoa, we got bacteria in here. And it's like, all right, we got to make sure that bacteria doesn't get absorbed into the body. Everybody out. And then all of a sudden you have, a really rough night on the toilet. It's very wet. It's, this wet, nasty mixture. That's because it wasn't formed into solids, because your digestive system got rid of it. It didn't absorb anything. And because there was no absorption, there was no dehydration synthesis, nothing got synthesized. So, those products are just getting out of the body. This is actually one of the reasons why, if you ever have the flu, which causes, a lot of diarrhea and stuff like that. One of the reasons why it's so very important to make sure you are drinking fluids like crazy. If you ever get food poisoning, guys, you should be drinking water like nuts, because it will dehydrate you substantially. You're losing a lot of water in this process. So something to be aware of. And we're done talking about pooping. All right, I do want to show you guys a little video here about the digestive system to kind of summarize everything I just talked about. Let's see, your digestive system. This is the one I want, right? Ooh, man, I think it's this one.
We all have our reasons for eating nachos at 3 in the afternoon.
Hold on. Yeah, okay, here we go.
We all have our reasons for eating nachos at 3 in the afternoon. I happen to have my own, and don't ask, it's personal. But more generally, we all eat any kind of food to accomplish two simple things: to obtain the energy we need to stay alive, and to get the raw materials required for building all of our tissues and stuff. That's because when it comes down to it, both you and the food you eat contain those two same things. Both you and food are made of stuff, by which I mean matter, made of certain kinds of atoms, and both you and food have energy stored in the bonds between those atoms. So all living things need to take in stuff and energy and convert it into slightly different stuff and energy. And you can get some of the things you need pretty easily, like in order to get oxygen for respiration, to unleash the chemical energy in your food, you just have to inhale. But you can't just breathe in the stuff you need to build DNA or actin or a phospholipid bilayer. So How does your body really acquire stuff? That's where the nachos come in. This cheesy, crunchy dish is made of all different kinds of biological matter like carbohydrates and fat and protein, and it contains a certain, probably shocking amount of calories, which is how we measure energy stored in the chemical bonds in food. So if I take like 100-calorie bite of nachos, which probably with this much cheese wouldn't even be a very big bite, I can convert the chemical energy stored in those carbohydrates and proteins and fats to feed my muscle and heart cells and maybe like walk a mile, an activity that happens to use about 100 calories. But I can't just swallow the nachos and watch the lump of them travel straight to my heart or leg muscles. In order to actually use this food, I have to convert the biological matter into something my body can work with on the cellular level, which, as you know, pretty darn tiny. And the work of converting the stuff in food into the stuff that's in my body is done by my digestive system. Human digestion occurs in 6 main steps, some of which you are intimately familiar with, others less so. But every step of the way, your body is working to reduce all the different kinds of molecules in food into their tiniest and most basic forms. The first step is probably everybody's favorite. When it comes to what your digestive system ultimately does, just think of it as a sort of disassembly line. You could have an order of nachos with the works. I'm talking beef and onions and sour cream and slices of jalapeno, and your digestive system will deconstruct it both mechanically and chemically, one step at a time. It's got to do this because your cells work best with materials that are in their most basic form. Your digestive system reduces food to that level in 2 main ways: by physically smashing it to smithereens and by bathing them as much as it can in enzymes. Enzymes are proteins that living things use as catalysts to speed up chemical reactions. When used in digestion, enzymes break down the large molecules in your food into the building blocks that your cells can actually absorb. Those large molecules are called biological molecules, also known as macromolecules, and everything that you eat, I hope, is at least partially made of them. And there are 4 main kinds. You got the lipids, the carbohydrates, the proteins, and the nucleic acids. Each possesses its own density of chemical potential energy or caloric value. Like, for example, 1 gram of carbohydrate contains about 4 calories, while a gram of fat contains about 9 calories. But many of these biological molecules are polymers, or sequences of smaller molecules, and your cells aren't really equipped to take them up whole. What your body traffics in are those polymers' individual components, called monomers, and there are 4 main kinds of those too: fatty acids, sugars, amino acids, and nucleotides. The simple idea behind the whole digestive system is to break down the polymers of macromolecules in your food into the smaller monomers that your cells can use to build their own polymers, while also getting the energy they need. And what your body needs to build at any given moment is always changing. Maybe you need new fat stores so you can have energy to run a marathon, or new actin and myosin to build bigger muscles, or more DNA so you can replace the skin cells you scraped off your knee when you fell, or more enzymes so you can digest more food to get more building materials. To meet your body's constant and constantly shifting demands, your digestive system requires a lot of organs that perform a lot of specific tasks to break down and absorb the right nutrient at the right time. Now, I'm quite sure that you're familiar with the key players here. They're the hollow organs that form the continuous tube that is your alimentary canal, aka the gastrointestinal tract, which runs from your mouth to your anus. It's worth pointing out that these organs are hollow because you are basically hollow too. Your digestive tract is really just one unbroken, insulated tunnel of outside that just happens to run through your body. Open at both ends. You're a donut. So the layer of stratified squamous and columnar epithelial cells that line your tract is actually a barrier between the outside world and your inside world, but it's a barrier that allows for the selective movement of materials between them. It's these hollow organs that do the actual moving, digesting, and absorbing of food, and they include your mouth, pharynx, esophagus, stomach, and small and large intestines. In your mouth, in your esophagus, and at the other end of things at your anus, you have stratified squamous epithelial tissue, just like your epidermis, to help resist the abrasive action of like chewing like corn chips maybe. From your stomach on down, though, the inner GI tract is lined with simple columnar epithelial cells, which secrete all sorts of stuff and which absorb and process various nutrients. Most of these columnar cells secrete mucus, which lubricates everything and protects your cells from being digested by your own digestive enzymes. So the innermost epithelial layer of the tube is known as the mucosal layer, and it contains some connective tissue as well, which supplies it with blood. Surrounding the mucosal layer is the submucosal layer, made of loose areolar connective tissue, which helps provide the elasticity that the tube needs when you eat a whole pizza in one sitting, and it contains more blood vessels. And outside that, you have the muscularis external layer, which, as you might guess, is where you find the muscles responsible for moving food through your tube. Beyond these layers, the GI tract gets tons of support from the accessory digestive organs like your teeth and your tongue, your gallbladder, salivary glands, liver, and pancreas. They're kind of like a pit crew, and they mostly help by secreting various enzymes that help take apart food as it comes down the tube. Together, these two groups on the digestive disassembly line work in 6 steps to destroy your food and release and recycle its nutrients. First, of course, you've got to introduce the food to your digestive system. What you know as eating or ingestion is basically just creating a bulk flow of nutrients from the outside world into your tissues. This is where the work of disassembly begins, in your face hole, which scientists call your mouth. Now, we're going to get into the details of what happens here another time, but remember that food disassembly is both mechanical and chemical, so your teeth pulverize the bite of nacho or whatever, while your salivary glands begin that food's hours-long enzyme bath. But the food at this point is not nearly micro enough to be of any use to your cells, so you have to move that mush further down your tube. This stage is called propulsion, and its initial mechanism is swallowing, which, as you know, is a voluntary action, but then it's quickly turned over to the involuntary process of peristalsis. In peristalsis, the smooth muscles of the walls of your digestive organs take turns contracting and relaxing to squeeze food through the lumen or cavity of your alimentary tract. Waves of peristalsis continue through the esophagus, stomach, and intestines, and they're so strong that even if you were hanging upside down while eating your lunch and drinking your tea, the food would still soldier on, fighting gravity, and eventually make it to its final destination. Don't do that, though. Other reasons why you shouldn't be upside down. Anyway, all of this shipping and handling mechanically breaks down the food even more, and even after it goes through the stomach and its gastric acid, the mechanical work still continues once it reaches your small intestine, as more smooth muscle segments push the food back and forth to keep it crumbling up. The goal of all this pulverization is to increase the surface area of that bite of food by breaking it down into increasingly tiny pieces to prepare it to encounter more enzymes in step 4, chemical digestion. Really, the actual process of digestion only occurs when the main action becomes more chemical than mechanical. And here, the accessory digestive organs, namely the liver, pancreas, and gallbladder, secrete enzymes into the alimentary canal, where they ambush the mush and break it down into its most basic chemical building blocks. Like I said before, our cells prefer to do business in the basic currency of monomers, like amino acids, fatty acids, and simple sugars, and digestion allows for the absorption of those nutrients as they pass from the small intestine into the blood by both active and passive transport. Once those nutrients are absorbed by your cells, you can finally use the energy inside of them or use them to build new tissues. The absorption of the nutrients is the goal of the entire process. But of course, it is not the end of it. Once your body has sucked out all the nutrients at once, indigestible substances like fiber are escorted out of your body. Yeah, I'm talking about pooping, or defecation. And that is the end of the digestive line, unless you are a capybara or one of the other animals who make sure that they get the most out of their lunch by giving the whole process another round and practicing coprophagia, aka eating their own poop. Now, you should notice here that some of the processes of digestion occur in just one place and are the job of a single organ. Like, hopefully you're only ingesting through your mouth and eliminating from the large intestine. But most of these 6 steps require cooperation among multiple organs. For example, both mechanical and chemical digestion start in the mouth and continue through the stomach and small intestines, and some chemical breakdown continues in the large intestine thanks to our little bacterial farm there. Over the next couple of weeks, we're going to take you and your nachos on a stroll through your digestive system and see who's doing what, where, how, and why. But for now, I got some nachos to finish, so I gotta go. And eating those nachos, as you learned today, will provide me with energy and raw materials by first ingesting something nutritious, propelling it through my alimentary canal, where it will be mechanically broken down and chemically digested by enzymes until my cells can absorb their monomers and use them to make whatever they need, and eventually they will be pooping. Thanks to all of our Patreon patrons who help make Crash Course possible through their monthly contributions. And if you like Crash Course and want to help us keep making videos like this one, you can go to patreon.com/crashcourse. Also, a big thank you to Peter Rapp, Sigmund Lervogue, Mikhail Moden, and Jeremy Bradley for co-sponsoring this episode of Crash Course Anatomy and Physiology. This episode was filmed in the Dr. Cheryl C. Kinney Crash Course studio. It was written by Kathleen Yale, edited by Blake DiFestino, and our consultant is Dr. Brandon Jackson. It was directed by Nicholas Jenkins, edited by Nicole Sweeney. Our sound designer is Michael Ronda, and the graphics team is Thought Cafe.
Okay. Any questions on any of the anatomic structures, guys? I know we've been through some of this before, but any questions about like how those structures work or what they are and stuff like that? Feeling good?
I'm good, bro.
All righty. Well, let's do the nutrition side of it. Okay, so diving into this is we're making a transition here. Diving into your NASM slides a little bit, looking at chapter 17, which is nutrition, right? So nutrition, so we want to be able to go over like an overview of like in nutrition, how it influences our body composition, things like that, performance, and just overall health. So we want to be able to describe like what our macros are and how what they compose in terms of our overall like energy intake. Talk a little bit about like certain nutritional recommendations that we're allowed to make, and dispel any dumb myths that are out there. So nutrition by definition is the sum of processes by which an animal or a plant takes in and uses food substances for growth and repair, which is a really technical definition to say, hey, it's how we take stuff from, it's how we turn food into us, or use it to do work and energy. So obviously a really big part of our industry, right? It allows us to integrate, nutritional information with our athletic performance. We can use nutrition to enhance our athleticism and bolster our results, right? Now, it should be noted that we definitely want to be familiar with nutrition because we are allowed to educate and teach our clients about nutrition. However, there is a distinction between our role in the realm of nutrition and that of a registered dietitian, which is a medically trained nutritional professional who focuses and specializes on like food and diet. So because they are medically trained, they are allowed to actually prescribe diets. So if your client comes to you and says like, hey, would you give me a meal plan? You can say, I can give you an example meal plan. But you cannot like customize and make them a specific diet. If you do, you are technically prescribing them to eat a certain type of food, and food in the United States is under the same umbrella as medicine. So you essentially just prescribed medicine, even though you're not a medically trained professional, which is against our scope of practice. So we are not allowed to do that. So definitely something to be aware of there. So talking about food and why, obviously, it's very important. We know that 75% of adults, U.S. adults, are overweight, or and a large percentage of that are going to be obese. And so here's the thing, when it comes down to like understanding weight loss and weight gain, it's actually pretty simple. Energy in versus energy out, right? If the amount of energy coming in is greater than the amount of energy going out, your body is going to gain weight because you just introduced energy into a closed system that has to go somewhere. It can't, first rule of thermodynamics says that energy can't be created or destroyed. It can just change from one form to another. So you can take a hamburger, and once it enters your body, you can either use all of its energy and burn it all up into like, mechanical work and body temperature and things like that. But if you don't, then whatever's left of that hamburger is going to get stored on the body. And that's, we measure that energy in calories, right? So if you bring in 500 calories, but you don't burn 500 calories worth of energy, let's say you burn 400, then that remaining 100 is going to get converted and stored inside of the body in another form, mostly in the version of body fat, right? So talking about that energy, right? Talking about how we measure that. We do measure energy using calories, right? And the calorie that we use every day, or the calorie that we're casually talking about when we talk about calories, is actually an uppercase calorie. That sounds really silly, but it is actually important because a lowercase calorie is the amount of temperature. It's the amount of temperature to raise 1 gram of water 1 degree Celsius. So if you took a single gram of water, a droplet, took a single gram of water and dropped it onto like a little beaker, and well, on like a little petri dish, and then you had like a potato chip, and you put that potato chip underneath, and you lit that potato chip on fire, and you had a little temperature thermometer in that 1 gram of water. However many degrees Celsius that water's temperature goes up is how many calories and how much energy is in that potato chip. Now, that would actually be really massive numbers. You would end up dealing in the hundreds of thousands if you were to measure it that way. And so because that's not very practical, we decided to divide the whole thing by 1,000. So that's where we got the uppercase calorie, which is the amount of energy required to raise the temperature of 1 kilogram of water. So that's 1,000 grams of water by 1 degree Celsius. And that makes the numbers a lot easier. Otherwise, you'd be looking at a nutrition label and be like, oh, okay, this has got 600,000 calories in it. When in reality, it has, in our world we live, that'd be a 600 calorie meal. So that is, that just makes the numbers much more manageable to work with. So it's the amount of energy to raise 1 kilogram of water, which is a cup about like that, 1 degree. So actually, how big is a kilogram of water? Yeah, it's a liter. Yeah. Yeah, it'd be like a 1 liter bottle. I was like, am I right about that? So that is about like this, actually. So it's however much, if you had a temperature probe in here and you were to raise this by 50 degrees Celsius, there'd be 50 calories in that food. So that's how we measure that, right? Now, that's how we understand the energy that's trapped in. And we just got to remember that we are constantly taking that energy in and converting it to either do work, right? We're burning it up to do physical work. So we're converting a hamburger into squats, literally. Or if we don't do work, then it gets converted into something else. So it'll get converted into maybe glycogen and then stored as glycogen inside the body if it was carbohydrates. Or it will get converted into body fat and stored as triglycerides inside of our specialized, what are called adipocytes or fat cells. So when we look at this, we want to make sure that we are in balance, right? Or maybe we're out of balance in order to gain weight, or maybe we're out of balance in order to lose weight, but we need to be able to manipulate the amount of energy that we're bringing in, and we need to have like targets in order to do that. So we have what is called your total daily energy expenditure, which is an estimation of how many calories an individual typically burns on an average day. So your total daily energy expenditure is how many calories worth of energy your body is going through every single day. So if you have like more energy coming in than that number that you are burning off, your body's going to gain weight. If you have less energy than your body is burning off, then you are going to lose weight. So that is how that works. Now, how do we understand, how do we know what our TDEE is? Well, it's comprised of 3 different things. It's, if we look at it, it's going to look something kind of like this. On average, right? You can see it's going to consist of 70% of it is what's called your basal metabolic rate. That is the number of calories that you burn simply by existing, So about 70% of the calories you burn every day are just from being alive, and just all the normal stuff to like, physiologic functions and stuff. Then there's a little bit from physical activity. Obviously, this could be a larger part of the pie chart if you are a very physically active person. So that is, the thermic effect of physical activity. And then there's the thermic effect of actually like processing food. Processing food takes energy. Your digestive tract's got to break all this stuff down and move it throughout your body. So that actually burns a little bit of energy as well. So when we look at it, right, your resting metabolic rate, 70% of your daily energy expenditures, the amount of energy you burn at rest. That's your RMR. This is sometimes called your BMR, your basal metabolic rate. Both of those work pretty well and pretty interchangeably. But basically, it's the amount of calories that you burn totally at rest, which none of us do. None of us are perfectly at rest. Then there's the thermic effect of food. That's the amount of energy required to process food. 6 to 10%, depending on like what your diet looks like. If you have like a really high fat diet, for instance, that burns a little bit less energy because fat just breaks down passively. But if you have a really high protein diet, that actually is harder to break down. So, you know, your thermic effect might even go up a little bit depending on like what your diet looks like. And then, oh, excuse me, there's the thermic effect of activity. That's the amount of energy during, you know, physical expenditure, right? Now, if you're super, super active, this is obviously going to be huge. You know, on average, I'm burning about 3,000 to 3,200 calories a day. I think in my normal life, and that's because like I exercise pretty regularly. Like yesterday, didn't burn that many. You know, yesterday was like a rest day for me, so definitely didn't burn quite as many calories. But you know, different amounts of calories depending on like what your client is like doing and stuff. If there was like, you know, there are days where I've been wearing like my little calorie watch and I'll go do like an ultimate frisbee like tournament or something. I went to this tournament in Phoenix and ended up playing like, it was like 12 games in a couple, you know, in over the course of like 2 days. And both days I burned like, you know, 5,500. I think I got close to like 6,000 calories. And I was like, good God. Like, it was just you know, it was just eating all day, you know. But that's where, you know, thermic effective activity is obviously going to outweigh RMR in some cases. You know, if you're a marathoner, that's a crazy amount of energy. So it is all just these are all just general, you know, observations, but everybody's a little bit different. So now taking a look at our nutrients here, you know, we are going to break nutrients down into a couple different categories, right? We've got our 6 essential nutrients. So these are going to describe our macronutrients, stuff we need lots of, micronutrients, stuff we need very little of, and water. So you've got your 6 essential nutrients, which I always like to kind of chart this out. I always think it looks really good as a chart. But if we look at like, you know, we've got our 6 essential nutrients, right? And then that's going to be comprised of your macronutrients. It's going to be comprised of your micronutrients. And it's going to be comprised of water. And so in your macronutrients, the stuff you need lots of, these are going to be your fats, your carbs, and your proteins. And in your micronutrients, that's going to be your vitamins and your minerals. And so that's kind of how all that breaks down, right? You know, if we look at it and it makes like a little bit of a kind of flow chart here, right? This is going to break down into these 3 things. This was a really pretty chart until I tried to draw this by hand. Right, and then micronutrients are going to break down into this and this. And so that's sort of what our 6 essential nutrients are. Fats, carbs, proteins, vitamins, minerals, water. There's your 6. So looking at that, breaking down like what protein is, because protein is probably the most famous of the one that everybody wants to talk the most about, because it's like, that's how I build muscle. It's how you build everything. So this is a big one, right? So this is a macronutrient that's really responsible for repairing the body's tissues. Your body is made of a lot of different proteins all assembled together, you know? So what a protein is it's a big complex chain of these chemicals called amino acids, right? Which is basically a little bit of carbon, hydrogen, oxygen, but then it's also got a little bit of nitrogen, which allows it to have all these really cool, funky looking shapes. So this is how we are synthesizing our hormones, the enzyme, you know, salivary amylase, that's an enzyme. Enzymes are proteins, right? All of those things that allow us to do like metabolism, you got to have protein in your diet in order to be able to do that. So there are these big complex chains of amino acids all assembled together in very interesting shapes. And when we eat protein, right, if we look at like a nutrition facts panel, just pulling up our random food here. There we go. So we look at whatever food this is. You can see it's got 5 grams of protein inside of it, right? So 5 grams of protein you know, that means there are 4 calories in every gram of protein. So we can go right there and we can say, okay, so 5 times 4, there are 20 calories in this food that are coming from protein, right? Let's total all this up here real quick, right? Just so you guys can see that this is true, right? So you got protein's going to have 4 calories per gram. Carbs are going to have 4 calories per gram as well. And fats are going to have 9 calories per gram. There's a lot of energy held in fats. So 7 times 9 plus 30 times 4. So that's going to be 120 plus 5 times 4, which is going to be 20. So that's going to come out to 203. I've done my math wrong somewhere. Or this is just mistaken. That's off by 50 calories. It's always off a little bit, but that's way off. 7 times 9 plus 120 plus, yeah, that's way off. And that's what happens when you Google stuff where the internet is clearly making stuff up. This is like a default, like they didn't pick this from a real food. Great. Nutrition facts panel. Milk. Actually, you know what? I'm gonna pick like a real. Okay, that'll actually work. That's like a real label. All right. So 5 grams of fat, 12 grams of carbs, 9 grams of protein. So that's going to be 5 times 9, so 45 plus 12 times 4. So that's going to be plus 48. Yeah. Plus 9 times 4. So that's going to be an additional 36. 129 calories. There we go. And there we see 130 calories here. So that is how they figure out how many calories are in food. Sort of. I mean, it's not perfect. You know, sometimes there are like little empty calories that are around. That's, you know, and they are allowed to do a little bit of rounding there. But generally, guys, if you're ever trying to figure out how many calories are in your food, you get about 4 calories for every gram of protein, 4 calories for every gram of carbs, and about 4 calories or 9 calories for every gram of fat. So protein, right? Like I said, big link of amino acids all held together. There's about 20 different amino acids inside of your body, and they're all, you know, if you arrange them in whatever order, that's going to determine what type of protein you've got. So whether it's skin, muscle, bone, hair, whatever. You know, those are different chains of those amino acids in different orders. So there are different types of amino acids in terms of how we classify them. You've got what we call essential amino acids, and you've got what we call non-essential amino acids. Non-essential amino acids are amino acids that your body can actually assemble. So if you have like sufficient protein levels, your body can be like, hey, I'm missing this amino acid and I need to make a new muscle cell. And it's like, all right, well, luckily I've got this amino acid that's shaped kind of similarly. So I can break that amino acid apart, reassemble it, and boom, now you've got the one that you needed, right? I always like to think of it as like a chef, you know, like if there's like a chef who's trying to make a meal and he's got like 20 ingredients that he needs in order to like make some type of food, you know, as long as he's got all 20 ingredients, he can cook whatever, right? And let's say those ingredients are garlic, salt, and garlic salt at some point, right? He needs all 3 of them for some reason. Well, if he doesn't have any garlic salt, but he does have garlic and he does have salt, he can take those 2 things, he can combine them, and boom, now he's got all 3, you know, different ingredients, and he can get to cooking. However, essential amino acids, your body cannot do this. So your body can do this with non-essentials. It can't do it with essential. That's why they're called essential. It is essential that you consume them in your diet. That's where they get their name. So they cannot be manufactured by the body. They have to be gotten through food. Now, how do you make sure that you're getting all of your amino acids? Well, that's where we sometimes classify proteins on like a food level, right? So we'll classify like a food as saying like that protein is a complete protein, or we'll say that protein is an incomplete protein. These are not good versus bad lists, by the way. They're just If it's a complete protein, it's a food that has all of those essential amino acids in it. And if it's an incomplete protein, that's a food that might be missing one or two of those essential amino acids. So, complete proteins are things like meat, poultry, fish, dairy, anything that came from an animal product is going to be an example of a complete protein. Because an animal's body like assembled all these amino acids together, so it has the whole profile. Incomplete proteins, vegetables, fruits, grains, legumes, things like that, those are all going to be examples of incomplete proteins. So for instance, like today, I've got like I made like burrito bowls for meal prep this week, and so like that's what I've got waiting for me downstairs. And it has beans and rice in it, right? So beans are an incomplete protein. Rice is also an incomplete protein. But when you eat them together, it makes a complete protein because they fill in each other's gaps. So you don't necessarily, this is where like, yeah, we hear about like people who are worried about like vegans getting enough protein. As long as they're getting plenty of protein from plant sources and they are pairing those proteins together effectively, there's no reason they're not getting a complete amino acid profile. So they are absolutely fine. Nothing to worry about there. So how do we determine how much protein to eat? How do we know how much protein we should be consuming? Well, in general, it depends on two main factors. It depends on your body weight, and it depends on your activity level. I always really get annoyed when I hear like people recommending diets and they're like, oh, you should be getting about 120 grams of protein a day. It's like, where did you come up with that number? Like, you could be right. Like they might absolutely be right. But like you just picked a flat number, like you know how much that person weighs, you know how physically active they are. If they're physically active, they're damaging their proteins more. Therefore, they need more protein in their diet. So exercise results in the oxidation of amino acid, breaks down your proteins, right? Damages your body. And so that means that we need to make sure that we've got plenty of protein in our diet in order to repair that. So it should be anywhere from 10 to 35% of your total caloric intake, or a really good way to think about this is to do it by body weight. So if you're sedentary, you're not really creating very much cellular damage. You're not moving around enough to break anything. So you're getting about 0.8 grams per kilogram of body weight, or about 0.4 grams per pound of body weight. But if you're a strength athlete and you're working out all the time, damaging your proteins like crazy, you might need all the way up to like 0.8 grams per pound. So like if you look at somebody like me, I need about 140 grams of protein per day, bare minimum, to make sure that I am repairing any of the damage that I created during my workouts. So that is where protein comes in. Now, high protein diets, which are diets where the amount of protein coming in is like 35% or greater of your total caloric intake, there's some side effects that come along with this. We see like increased urea production, which means that your body odor is going to smell pretty bad because you're making way too much urea. It can result in dehydration because proteins need to be broken down with hydrolysis. So it takes a lot of water in order for that to happen. Generally, if you are getting so much protein, it's probably coming from sources that may be very high in saturated fat, which we know is linked to heart disease. And it can result in decreased glycogen stores because you're not getting enough carbohydrates in your diet. So a lot of negative stuff here, right? Not so awesome if we have like a super high protein diet. But that being said, proteins are extremely essential. You do want to make sure you're getting, at least enough of them. Now you've also got carbohydrates, another one of our macronutrients. This is the one that is your chief energy source. Our body prefers to use carbohydrates for energy over any of the other macronutrients. So, macronutrients, in the same way that proteins were big complex chains of amino acids, carbohydrates are big complex chains of sugars. They're complex chains of what we call monosaccharides, single sugar molecules. So they get about 4 calories worth of energy in every gram, just like protein did. But these we need in much higher levels. We want to get about 45 to 65% of your calories every day coming from carbohydrates. So we're going to classify carbohydrates in a couple different versions here. We're going to have our simple carbohydrates, which they're simple because they're already broken down. They're basically just sugar molecules, right? So sugar, like table sugar, that's a disaccharide. Honey, that's a disaccharide. Fruit, the sweetness in fruit is very much a disaccharide. So those are all very simple carbohydrates. But we've also got complex carbohydrates, and complex carbohydrates are big, long, complicated chains like potatoes, starches from like grains and breads and things like that, oatmeal, right? All of that stuff. And then we've got the super complex, which is like, you know, so very complex that our body actually cannot break it down. And that's your fiber. And so fiber is the types of carbohydrates that are so complicated your body literally cannot break it down. The chains are just way too complex, which is a good thing, because that means that it's going to pass through our digestive system and it's going to kind of act like pipe cleaner. It's going to grab anything that's sitting around in there. And it's going to pull it out of the body. So those are that's our carbohydrate classifications in a nutshell. Now, the reason they're, you know, sometimes given a bad rap, simple carbohydrates are very easily digested. And so, you know, when we talk about like why sugars are so bad for us, they spike our blood sugar levels. They massively elevate our blood sugar levels in a very short period of time, which when that happens, triggers your body to generally store it as fat, because it's like, wow, we have way too much energy and we can't burn through all this so quickly. Store it, right? So it converts it into glycogen if it can, but generally it converts it into adipose tissue because there's just so many grams of carbs in such a very easy to break down and very tightly compacted area. But it tastes really sweet, so there's that. You know, it's delicious, you know. Then we've also got our complex carbohydrates, which are the ones that take a lot longer to break down. They impact our blood sugar levels a lot less. So one of the reasons why we got to make sure that we encourage diabetic clients to consume complex carbs rather than simple ones is because we don't want to spike their blood sugar levels. We want to bring their blood sugar levels, up slowly and steadily. And that way, their blood sugar levels don't spike and drop, the faster something climbs, the, faster it's going to fall, And then fiber. Fiber is so very important. We need to make sure diets that are high in fiber have been shown to reduce your risk of heart disease. They reduce your risk of certain types of cancers. In general, guys, they're going to recommend about 25 to 35 grams of fiber in your diet per day. This is important for everybody. It leads to you feeling fuller for longer because it's harder to digest, so it's in the way, slows the process down a little bit. It provides bulk to your diet, and it regulates the absorption of that glucose. We're not going to spike our blood sugar levels as much. So huge fan of getting fiber in. Best sources are going to be whole grains. I really love, like cereals that are really high in fiber. It's one of my favorite ways because I love cereal. You guys see me eating a bowl of cereal every morning when I'm on these calls. That's like I drink a protein shake after I'm done working out, and then I go eat a bowl of cereal. And that bowl of cereal is me restoring my glycogen so that I have energy for the rest of the day, and I also just, I feel like I have to have it in the morning, just grow up my whole life eating cereal. So we know that carbohydrate intake is linked to increased performance when it comes to athleticism, right? So we see like anaerobic activity, like high intensity, short duration activity that generally relies on carbohydrates as a fuel source. So we want to make sure that we have plenty of glycogen inside of our body. Aerobic activity, which is your long duration stuff, really here you're actually going to probably end up where glycogen's only supplying maybe 50% of your energy, whereas the rest of it is coming from your body fat. That's your much low intensity stuff. So high intensity stuff burns carbs for fuel. Aerobic stuff burns carbs and fat for fuel. And then like super aerobic endurance based stuff, generally fat is actually supplying like a lot of energy there. But you still want to have like 60% of your calories coming from carbohydrates in a diet like that, because carbohydrates are burning in the background. You essentially have an unlimited amount of fat stored, in terms of energy inside of your body. The amount of calories that you have stored in your body as like fat tissue is crazy high. So if we want to make sure that we have like enough energy to do stuff, we need to make sure that we have plenty of carbohydrates burning in the background there. So we don't ever lose that high intensity. So in general, what NASM and most people are going to recommend is you want to get a good high carbohydrate meal 2 to 3 hours before any event that's going to last 60 minutes or longer. So if you're going to lift for 90 minutes, you know, which is about as long as you want to lift, by the way, that's really long. Your workouts really should be about an hour 15. You know, carbohydrate drinks actually might be a really good option for you because they can sort of, you know, keep those sugar levels neutral. Now there is like carb loading schedules for those of you who might partake in like marathon training or things like that. Anything that's greater than 90 minutes, like I said, it's going to deplete your glycogen stores. So you want to use carbohydrate loading to hopefully increase your muscle glycogen stores before like a competition or something, right? So basically what that's going to look like, you're going to pair up a little bit of working out with a little bit of like high carbohydrate consumption. And that is going to signal to your body that it should store carbohydrates more effectively. So about 6 days out, you want to do a relatively, relatively medium intensity activity for about 90 minutes and consume about 4 grams of carbs per body weight, which is actually not very much. But what that does is that actually makes your body very hungry for carbohydrates. Do something similar about 4 to 5 days out, but you shorten the duration, keep the carbohydrate intake relatively low. And then about 2 to 3 days out before your event, you do a very little physical activity, but you maximize calories coming from carb. You just go carb crazy. Like, hey, I got you some pasta to go with your bread. And you just carb it up like crazy. And what your body does, because it's kind of been hungry for those carbohydrates this whole time, is it goes into massive glycogen storage mode. And then that's going to give you plenty of energy when you go run your marathon or something. And really that's who this most applies to. You know, most of the time we're talking about carb loading. We're talking about marathoners or triathletes and stuff like that. So any exercise, like I said, greater than 60 minutes, you're going to want to make sure that you're getting plenty of carbohydrates in. You can also consume like a glucose drink, you know, like a Gatorade or something, which is sugar water. That can help, restore glycogen like on the go. You can also do this, like one of my favorite methods is just to have like a small snack right before I'm heading into the gym. Something that's carby. And then after exercise, you know, you always think about like, okay, carbs before, protein after. You kind of need carbs after your workout too, actually, because again, you just depleted all your glycogen stores. So you want to make sure that you get those refilled, not so much for the workout that you just did, but for tomorrow's workout, because you got to do it all again, right? So we want to make sure that we are restoring our glycogen stores after we exercise by getting plenty of carbohydrates into our diet. Now, when it comes to altering your body composition, whether that's weight gain or weight loss, honestly, carbohydrates, and really for anybody, I mean, all of our clients, should make up the highest percentage of carbohydrate, of macronutrient intake, you know? We recommend anywhere from 45 to 65% of your total caloric intake coming from carbohydrates. There's very little data that suggests that like carbohydrates are what lead to obesity. I know that like we are in the middle of like a low carb craze right now. But as long as they are complex carbs, the likelihood that carbohydrates are what are making you fat is relatively low. Sugars, not great. You know, sugars we want to avoid. But complex carbohydrates are complex and they have really good properties. Then we got our lipids here. Lipids, the fats inside of our diet, right? So these are fatty acids, right? Big complex chains of fatty acids. And they're going to exist in 3 primary forms: your sterols, triglycerides, and phospholipids. So sterols are things like your cholesterol, right? These are produced by your liver, but they're also obviously available in food. And so when you think of like these are your lipoproteins, right? So you have got low density lipoproteins and high density lipoproteins. And so Low density lipoproteins are what we call the bad cholesterol. They're not very dense, so they often get stuck in your blood vessels, and then they start building up on one another, and that sort of fills that blood vessel with what we call plaque. And then that decreases blood flow, which raises your blood pressure, which makes your heart perform harder. All bad stuff here, right? So that's your bad cholesterol. That's your low density lipoproteins. But then we have the good stuff. We have the high density lipoproteins, right? This is your good cholesterol. These are, they have a high percentage of cholesterol that has like plenty of like intense proteins that are really, really, really dense. So they go in and they, clean out your blood vessels. So generally, the low density lipoproteins are associated with your saturated fats, and your high density lipoproteins are associated with your unsaturated fats. So that's why, we usually split those. A lot of your fats, you want them to be liquid at room temperature. Olive oil is just a great example. Avocado oil is one of my favorites. All of those are really, 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 really good for us. So then we've got our saturated versus our unsaturated fatty acids, which are different from these cholesterols, although they are often tied together. But, we look at it, it's three little fatty acids, one here, here, and here, attached to this little backbone of glycerol, right? And so triglycerides are what we metabolize for energy. We break down triglycerides and, break them apart so that we can use them to release their energy and do stuff. So when they're metabolized, they can be converted into glucose, and they can be, used to produce energy. That's where you talk about somebody who's on keto. They don't need any carbohydrates because their body is converting fat into energy instead. So the two major categories of fat, like I said, you've got your saturated and unsaturated. The saturated fat is solid at room temperature. These are things like your butter, lard, animal fats, coconut oil, stuff like that, versus your unsaturated fat, which is, the oil stuff, right? And the unsaturated fats are usually associated with the good cholesterol, whereas the saturated fats are typically associated with the bad cholesterol. And generally, we want to focus on we like them both, like mono and polyunsaturated fats. All of them are actually very good for us. But generally, we want to have a good ratio of mono to poly. So we do want to have like a good mixture of fats in here. And that's why I really like to make sure that I always have some type of nuts or seeds in my diet, in addition to a lot of the olive oil that I cook with and add to my foods and stuff. And that's just a really good way to make sure that I'm balancing out my fats. There are some implications to, if you get a really bad mixture of your fats, you get a really bad balance, it can cause inflammation inside the body. This is why fish oil pills have been shown to have people will take fish oil pills, which is a polyunsaturated, healthy fat. And it's what we call an omega-3. And that has been shown to be very good for joint health and stuff. So in general, your lipids are going to have, like I said, they're going to have 9 calories per gram. They're a little bit denser in terms of energy compared to with carbs or protein. And we want this to be about 20 to 35% of your caloric intake, because low-fat diets have been shown to be kind of dangerous sometimes, because you remember, you got to use your fats to transport fat-soluble vitamins. When I talked about vitamins A, D, E, and K earlier, those vitamins are absorbed by the body, and they're carried through with fat molecules. Without that fat in your diet, you might be vitamin deficient, which is crazy. That's also why I tell people, if you're making a smoothie, add a tablespoon of olive oil to it. That's a really great way to boost your fat content in a really, really healthy, positive way. So again, fats really important. They're precursors to our hormones, especially things like testosterone and estrogen. They protect our organs, and they prolong the digestive process. Fats leave you feeling full longer, which is really, really nice. So 20 to 35% of your total caloric intake is the number you guys need to have memorized. All right, so talking a little bit about moving outside of the macros here, and just talking about when we're giving our clients dietary tips, right? Part of being on a diet is dealing with like hunger, which is a real pain in the rear, you know? So we got to make sure that our clients are feeling satisfied. So digestion of fat is really helpful because it starts breaking down in the fat and releases these hormones that signal satiety. It releases these hormones that make you feel full. And then medium chain triglycerides, MCT oils, are another really good example of this. They can also be used directly for fuel. Uh-oh. My internet's being a jerk. Sorry, guys. Can you guys hear me? Am I lagging? Everybody still here? Oh, we did lose Jericho. Well, crap. So MCT oil, you've probably seen that at sold in stores and stuff. It's a really great thing that can be added to your food to be metabolized and leave you feeling fuller for longer. Getting really popular in the last few years. You know, when it comes to like growing your fat cells, right? What happens is like just breaking down like what happens during like a fat cell growth, right? The growing fat cell becomes like insulin resistant, right? So we look at like how like people gain weight in this kind of vicious cycle, right? So remember, insulin's job is to pull sugar out of your blood and either store it as glycogen or convert it and store it as fat. And so if you've got a fat cell that has become resistant to insulin, it is going to need greater levels of insulin in order for that to happen. So what ends up happening is you create a huge amount of insulin, and finally that pulls all the sugar out of your blood. And then you have like a major hunger craving, right? And so what ends up happening is you end up consuming probably a massive amount of carbohydrates again. And then that creates this vicious cycle with the overweight condition leading to insulin resistance, which in turn leads to impaired glucose control, which in turn leads to greater levels of hunger, making it harder to like stay on your diet. So, you know, this is why like high fat, high sugar diets are strongly associated with obesity, because they often cause, you know, insulin resistance, which is very, very bad for us. Now, the last thing that we want to recommend that our clients do when it comes to like consumption of nutrients and stuff, the most essential nutrient that we are going to consume is water. Water is hugely, hugely important. So this is transporting materials throughout the body. It's balancing our pH. In general, guys, these numbers, and you want to have these memorized, we want to get about 3.7 liters per day for our male clients and about 2.7 liters per day for female clients. So that's about a gallon for guys and about 3/4 of a gallon for women. So trying to get that water in there every single day, hugely important, because it makes our cells healthy and balances out our pH, moves tissues around, and helps us like regulate body temperature and stuff, which is really nice as well. You are 60% water, right? If you lose just 2% of your body weight, your body will perform poorly. So we need to make sure that we're getting plenty of that water back in. It's going to help improve our hormones, appetite, body fat percentage, blood volume, body temperature, so many really good things. When you are dehydrated, you have less blood, which means your blood is thicker and stickier, which makes it harder for your heart to pump blood around. It will decrease your performance because you're not delivering oxygen to your cells very effectively. It will decrease your blood pressure in really negative ways. It'll decrease your cardiac output, the overall performance of your heart. So again, decreased performance there. It'll increase your heart rate because, again, your stroke volume goes down, so your heart rate has to go up. And it will increase the use of your muscle glycogen, which will raise your blood sugar levels, which again could result in impaired glucose control. So we got a million different ways to get diabetes, right? One of them is actually not drinking enough water, which sounds very surprising. So try to get anywhere from 14 to 22 ounces before any activity that you're going to do. And then every 15 to 20 minutes, try to drink about 6 ounces of water. That's really not that much. That's less than a coffee mug. So, and then we generally recommend drinking cool liquids because it'll slow down how quickly it leaves your stomach, again, leaving you feeling fuller for longer, but I think that's personal preference. If it's less than 60 minutes, water is going to be your best choice. But if your activity is greater than 60 minutes, NASM is actually going to recommend things like Gatorade, because that's going to have a little bit of carbohydrates and fluid in it. So you're kind of killing two birds with one stone here. Now, in terms of like altering your body composition, right? When it comes to, general tips that we want to give our clients, this is sort of a short list of some of the best tips you can give your clients. I'm going to go through each and every one of them. First tip, make small decreases in your change as you increase your physical activity. Do not try to make a huge, big lifestyle change all at once. Generally, that is hard to stick to, and you're more likely to fall off the wagon. So smaller changes are much more sustainable than fast changes. Try to distribute your proteins, carbs, and fats evenly throughout the day. Get a good mixture of all of them. The one little asterisk that I'll put next to this, if you are very serious about your strength training, I would keep fat away from your post-workout meal. That's the only like little small tip that I have, just because fat kind of slows down the absorption of protein. This is why protein shakes work so well, because they take that away. Then suddenly it doesn't matter, because that stuff is so quickly absorbable. So if you're not doing a protein shake and you're just doing a meal after your workout instead, try to make it a generally like low fat meal. But that's the only time I'll say that. Fat is incredibly important to have in your diet. Very, very good for you. It just slows down protein absorption slightly. Choose whole grains and fresh vegetables rather than refined grains. So whole wheat bread rather than white bread. Fresh vegetables over simple sugars. Avoid empty calories and processed foods. We want to make sure that we are focusing on nutrient dense foods, not energy dense foods. Try to get your water recommendations, 3.7 to 2.7 liters per day, and measure your food. Get used to like how much energy is actually in your food. Get used to using a food scale. It's one of the most effective, helpful tools available to you. I love using my food scale. It's a great way for me to very quickly be able to manage, how many calories I'm bringing in and stuff. So when it comes to altering body composition for lean mass gain, if you're trying to bulk up and gain muscle, generally you want to consume about 4 to 6 meals per day. Try to keep your protein spread out. Generally use like a protein or carb drink within 90 minutes of exercise. Again, the protein to repair the body, the carbs to make sure you're ready for tomorrow's workout. And remember that carbs and fat are still important. A lot of times, like people who are trying to gain weight are just like protein with more protein, blah. And it's like, keep the carbs and the fat in your diet. They are still important. All right, and then the end here, I love this. We got a rapid fire short list of dumb questions. Do carbs make me fat? No, carbs are very good for you. They are totally necessary. They are high in fiber. They regulate your blood sugar levels. But consumption of like processed carbs could lead to increased sugars, which could lead to increased energy, and excessive energy makes you fat. Does eating at night make you fat? No, it does not matter when you eat. Weight gain is a result of too many calories, not when those calories are consumed. Which is better, low fat or low carb? It doesn't work that way. Both of those versions are dumb. So weight loss is achieved when you are eating less calories than you're consuming. That's what matters. Can I eat whatever I want as long as I exercise? I love this one. Can you out-exercise a bad diet? No, you cannot. When it comes to weight loss, it is generally about 70% diet, 30% working out. So very, very important to make sure, it's all energy balance, right? What if I go on a starvation diet? Will that work? Like, what if I do like a, low calorie diet? You could, but it's probably not a good idea. That could lead to malnutrition. You're not going to get enough vitamins or minerals. It could lead to poor energy. You might feel bad and tired all the time. It can leave in a behavioral pendulum, where you're ready to murder someone, then you're fine, but then you want to murder them again. It can lead to fatigue, constipation, diarrhea even, because your body just is trying to signal you to get food. And Starvation diets can often lead to gallstone formation. So super low calorie diets can sometimes actually cause gallstones. What about high protein diets? Is super high protein more superior for muscle gain? Not really, because you can only absorb so much protein at a time for protein synthesis. So you need about 1.2 to 1.7 grams per kilogram. That's the same that we saw on that chart earlier. I didn't put it up here. So 0.5 to 0.8 grams per pound, right? So diet, really, really important. Obviously, a great way to ensure that you are positively affecting your results. Pairing it with exercise is just a great way to enhance everything. Proper nutrition, very, very important, especially for us as fitness professionals. We need to be able to have these conversations. But you'll notice, for those of you who have been through some of these conversations before with me, they all kind of circle back to the same thing pretty consistently. It's the same message over and over again. Energy in versus energy out, whole foods rather than processed foods. And that is it, guys. Double PowerPoint again today. I don't think that's the case tomorrow, if I'm not mistaken. Yeah, just the one tomorrow, so it'll be a little gentler. But we are going to do metabolism again tomorrow, which will be fun. Any questions, comments, concerns? How y'all feel? We lost Jerica. Andres, Charlie, Cody, how you guys feel?
I'm good, Brad.
All right, fair enough. Well, guys, that's about all I got for you. I'm going to go ahead and end the recording, and I'll see you guys tomorrow.